Hi, my name is Michael Lerner. I teach physics here outside of Cleveland. I teach all AP physics, and I use modeling techniques in my classes. I started with modeling in 2013, and I'm here to talk to you about how I use system schema or interaction diagrams to have students solve really difficult problems. For this video, I'm going to use the ballistic pendulum as a difficult problem because it's a problem that most physics teachers know about. The ballistic pendulum causes a lot of problems for students because it requires them to use more than one model, and knowing when to use what and why is difficult. Also, depending on the information you give them, they might have to solve the problem forwards in time to figure out how high it's going to swing up, or backwards in time to find the initial velocity of the ball that's launched. This can be really difficult for students. What I found help is that I used system schema, or what I call interaction diagrams, a lot in my class. I learned about system schemas in my modeling workshop, but I know that some people don't see that in the curriculum materials. If you don't know what they are, go look them up. They're amazing. But what I find really helpful is they're helpful in all of my units, and I can show how they can be used for a difficult problem like this. Let's start with what's going on to begin with. You can see at the beginning, we have the sphere and the launcher are touching, and the pendulum bob is being held up by the string. Now, this is a simplified version. There are other interactions we're not keeping track of, but you can see that I have these interactions hooking up the objects, and everything's sort of at rest. Then the launching happens. You get an elastic interaction between the spring and the sphere. This is sort of when the ball is being burst out of the gun. Then, which is something we don't normally talk about, the ball travels through the air. The sphere is just falling due to the force of gravity. And then there's a collision with the pendulum bob. And then the pendulum bob and sphere, in my mind, become one object, so they become one circle, and it swings up. You'll notice I've drawn a lot of different interaction diagrams to explain this. Every time the forces in the situation, the interactions in the situation changed, I drew a new diagram. And every time you draw a new diagram, you need to think about the problem anew as something to solve. This idea of thinking of something as made up of lots of little bits that add up to a whole makes a lot of sense in the TikTok generation, to make myself seem old, because they're used to videos going very quick scenes. And so I actually call these scenes. I would have called this scene, scene 0. It's the sort of setup scene. And in this case, everything's at constant velocity. It's a great thing to use a model for CVPM. In this new scene, now I have an elastic interaction happening, and those are difficult to model with forces. This seems like a good part to model with energy. So this is where we'd model energy. We have a beginning where everything was at rest, which was the end of the last scene. And then I can figure out what's going to happen to the velocity of the sphere at the end of this scene. And the end of this scene is the beginning of this scene, where the sphere is traveling through the air. Personally, this is something that I think of as negligible, which is a word I love using in my modeling physics classes because it means it's there, and depending on how exact you want to be, you need to use it. But in this case, we're going to ignore it to see the deeper structure in the problem. I consider this a CVPM part of the problem, but I could understand why other teachers would not think this is a constant velocity part. Then there's a collision. And boy, does that scream momentum to me. That normal force is quick and sharp and way large. And we know that the momentum is going to be conserved in this problem. And then the object swings up. And we can see the gravitational potential energy increasing of this system and the kinetic energy of this system decreasing. Having kids write out these scenes and then thinking, oh, okay, now I can figure out what model I'd use with each one of these scenes is a great first step for figuring out what to do next. And I think that one of the things I'd love to do at some point or see somebody else make is a way of capturing 5 or 6 of these interaction diagrams really quickly on a computer so they can change them really quickly. Boy, was this easy to draw on a computer. I just had to change one interaction at a time. But having kids laboriously draw them out can be difficult, which is why a lot of times my students stop drawing the interaction diagrams. But boy, does it help to say, like, when does the interaction change? When does a new force enter or a force disappear from being relevant in the situation? And therefore, how do we have to use a new model? And you either go through each one of those scenes in order and taking the end of one scene as the beginning of the next, or you have to go through them backward. I hope that helps.